Thanks ASC Computing and Civil Engineering Conference to give me the opportunity to present my research on this platform. The title of my research is Estimating Output Variance of a Regressing Model Tree, and we did an application case on developing concrete strength prediction model. I myself is Manjurul Hassan, a PhD candidate at the University of Alberta, and my co-author is Dr. Ming Lu from University of Alberta, Canada. Machine learning techniques are very popular nowadays in preparing predictive models for various civil engineering applications. Models are prepared to take inputs and process those to generate outputs. Major limitations with such a model are model itself remains a black box, doesn't explain the reasoning behind the decision. In addition to that, model only provides the point value output. The uncertainty associated with the prediction is missing. As a consequence, the model loses trust from the practitioners. To overcome these limitations, we need to have a machine learning model that can explain the reasoning behind the decision. Also, need a model which can provide an estimate of the uncertainty associated with the prediction. Solving those two problems would increase the usability along with the reliability of any such machine learning model. Regression problem. Linear regression or multilinear regressions are the widely used machine learning model. It is easy to interpret since model is basically a simple linear equation where model's input-output relationship is explained by the slope beta of the linear equation. However, it is not a good fit for nonlinear input-output relationship. Now, what model tree is? A model tree breaks down the whole dataset into small subsets appropriate for explaining the input-output relationship with regressions. Each subset is defined by a set of binary rules on top of the model input attributes. For this example, as shown in the previous slide, the nonlinear dataset is divided into three subsets. Each subset is defined by the range of values of input attribute x. Now, the input-output relationship for data confined in each subset of three can be explained by linear regression equations. So, model tree can explain nonlinear input-output relationship. However, variance estimate associated with the predicted output is still missing. The enhanced version of the model tree should have provide both of them. Here is the basic equation of a multilinear regression model. The problem investigation starts with defining the mean and standard deviation of the slope parameter of a MLR equation, since it is the end form of the model tree type model. For example, if we want to establish a linear relationship between x and y, process starts with selecting a subset of data randomly chosen from a dataset to capture the xy linear relationship with beta as the slope and beta naught as the intercept. Now, if we take another subset of data and get the linear equation, I will find a different set of slope and intercept values. Running the same process n times will help to generate n slope and intercept values. N set of beta 1 and intercept beta naught can generate mean and standard deviation of beta 1 and beta naught. Here is one example with the data. For any MLR equation, this process can be used to define the beta with mean and standard deviation. Also, as soon as the statistical description of the linear equation is defined, that means the beta parameters are defined, the error propagation model then can be applied. The propagation of random error basically follows the laws of propagation of variance and covariance and can be expressed by this equation. Cy is equal to zxy, cx z over txy. Here, Cy is the covariance matrix of output y and Cx is the covariance matrix of input x. Zxy is the Jacobian of the equation relating x to y. Here the equations to define Jacobian and covariant matrices are given over here. So the basic MLR equation or multilinear regression equation is shown in equation 1, and the variance of y can be found using this equation, equation number 2. Now, for a set of given inputs, mean of the prediction y can be found by plugging in the mean values of beta in equation 1, and variance of the prediction y can be found by plugging in the variance of beta in equation number 2. So, in enhanced model tree version, the new algorithm combines the model tree algorithm with the variance analysis model that I showed just right now to enhance its capability to predict the variance estimate of the predicted output along with the prediction, which means uh, basically which we name as the model tree. But to demonstrate the application of the new enhanced model tree, we used concrete strength prediction modeling case. The dataset was taken from University of California, Irvine Machine Learning Repository. Total 1030 instances with 8 attributes denoting high performance concrete strength case was used for this purpose. Here are the attributes that we used, where X denotes the input and Y denotes the output. Model first identify different classes of data to develop linear input-output relationship, where data classes are defined by a specific set of rules represented like tree branches as shown over here. Input data which satisfy the rules of each branch should have a similar equation to predict the compressive strength for a given set of input, and a variance model which gives the associated variance estimate of the predicted output. For this example case, a total of 8 model tree rules or rule branches were found. Rules and equations for first 3 branches are shown in this table. Model performance. Actual concrete strength results are plotted against the model's prediction, and in the first figure, the coefficient of correlation over here is 0.9, which is pretty good for practical applications. Also, the predicted output is always within the acceptable limit, as shown in figure number B. This acceptable limit is established by the estimated variance associated with the predicted output. For this example case, the output threshold is set to 1.96 times of the standard deviation or the square root of the variance estimate of the predicted output. To conclude this research, we enhance the model tree algorithm, which is a transparent model interpretable by rules, can capture nonlinear input-output relationship, gives the variance of estimate along with the predicted output. Thanks for listening to me. If you have any questions or want to know more about the research, please email me at mdmanjur@ulberta.ca or Dr. Minglu mlu6@ulberta.ca.